Well, hello there. It's the weekend. Let's make hay while the sun shines, right? Or more like make triangles while the sun shines. We can actually say the hello world for graphics, which is a triangle. Now, before we actually draw the triangle, a few things have to be done. We need to tell the GPU how to draw a triangle. Yes, how to draw a triangle. Of course, it's more on the lines of just giving it, okay, vertex 1 is here, vertex 2 is here, vertex 3 is here. But that itself is quite a big thing to do. So we're going to do it in small steps. We're not actually going to tell the GPU where the vertexes are manually. We're just going to hard code the vertexes inside the program, and we will just, index it in. But what program is this? This is not C++. So we need a different language, a shader language as well as, to run programs on the GPU. There are many of them. And Vulkan is quite ambiguous about this in the sense Vulkan has support for an intermediate language known as SPIRV. That's Standard Portable Intermediate Representation 5. And any language that can compile to SPIRV is good for the GPU, like for Vulkan. You have languages such as HLSL, high level shading language. It's the one DirectX uses. That can also compile to SPIRV now. And in fact, I think there is plans for DirectX to support SPIRV directly, which means you won't have separate HLSL compilation requirements between Vulkan and DirectX. You'll just, compile to SPIRV. There is GLSL. So that's for OpenGL shading language. Vulkan can use that. In fact, all new Vulkan extensions are directly supported into GLSL using extensions, but the language itself is pretty archaic and it doesn't really get developed anymore because OpenGL has become sort of archaic. The new kid on the block is Slang. So we are going to use that Slang. It is industry vetted. All the shaders at Valve. So any game released by them, Half-Life Alyx, Counter-Strike 2, they're probably Slang shaders now. So this is how a shader program looks. I've just written it anyway. In fact, I was doing it on screen, but unfortunately, I had my mic on mute. In fact, I should probably check if I am audible or not. Okay, it seems like I am. So what is happening here? We're going to just look at parts of the code in their independence. This, ignore it for now. Just look at vertex main. So this is a function, just like we do on the CPU. uint, which is unsigned integer, vertex ID, but it's just a name. This tells us what the parameter is supposed to do. Okay. Certain objects, certain things are unique. They are inputs that are available to us that are just provided by the GPU, right? In this case, each vertex shader function gets run on a per vertex basis, which means each vertex is completely independently processed from another vertex. So how does my vertex number 2 know that it's vertex number 2? This is done using SV vertex ID. It gives an ID to each vertex per dropal ID, that is. Similarly, when you output something, this goes back to the GPU. GPU does some stuff with it, like it streams it into the streaming processes if you're going to use it more, or it goes to the next stage. So if you're using tessellation, then it will go to the tessellation shaders. Then it will go into the rasterizer. We don't have much control over it. The rasterizer will create the triangles. Then each of the fragments in these triangles. Fragments are similar to pixels. The only difference is when you use multi-sampling, so anti-aliasing, for example, that would have more than one fragments in each pixel. And so all 4 of them need to be shaded separately. That's why anti-aliasing is more expensive. At certain points, it will do 4 times as much computation as a normal shader would have done. All of these fragments go to the fragment shader. We'll come to that. It's here actually. And that will process it into the pixels that you'll see on the screen. Well, actually, it will also produce fragments. And then there'll be a resolve, which is not a shader again. And that produces the image on the screen. So when we produce this set of vertices, we can also give other data. This other data can be available to the fragment as well. But the rasterizer cannot handle it. Rasterizer is fixed function. It has very fixed definitions for things. So what it will do is it will look for SV position. And so we add that here. These have different names. This is SV position in HLSL. In GLSL, I think it's called vertex pause, GN vertex pause. But anyway, these can be structures instead of just inputs and outputs, but we're leaving it as inputs and outputs for now because it's simpler for us to track it like that. I will, however, indent it in a easier to track fashion. Oops. Okay. Anyway, now fragment shader takes as an input the location of the fragment. Okay. This position is screen space, but it's also interpolated. So for each fragment, it will interpolate between the vertices to get you the actual position that it creates. And similarly, any other outputs that vertex main has will also be interpolated. So fragment shader gets float 4, which is the position. So we call it screen position. Just call it position for now. And this comes from SV position, right? So we will write that and it will actually give us that SV position here. Generally, this position and the one from the shaders are separated because of processing reasons. But right now, again, we kinda don't care. The float for out here is a color. This is SV target. Okay. Target 0. So SV target is an output to the screen, to the target on the screen. Since we created the swap chain images yesterday, we actually tell what our target is. So that's the rendering attachment. And you can have more than one. As you can see, we have said there's only one, but we can have more than one. And so the target can be more than one. So we say target 0 specifically. You can just say target, but I keep target 0 because it's explicit in respect to what it wants to do. And you return the position, okay, dot RGB. So that's a swizzle. Oh, it doesn't support it. Oh, no, it does support it. It's just a thing. So I ask for RGB and then I provide alpha separately because I want alpha as 1.0. And now it works. So this is known as a swizzle. I can do R, G, B, and A, and I can access them as RGB and ARGB and BGRA or like whatever combination of those letters I want, even X, Y, Z, W, and then, move those around. And it will produce an output that has those components in the right place. We just need RGB right now. And I'm calling it RGB because it explicitly says that this is a color. You can say XYZ. It's the same thing. You can see the automated prompt actually saying this is XYZ, but I like writing it with the more semantically appropriate things. So that is our shaders. This should compile normally. We can test. It has compiled. Great. We'll go back to the Blaze main thing. And once the shaders have compiled, we actually need to get these to the GPU. Now, one of the things that we did was creating all of these per frame objects. Pipelines, which is what the shaders are composed into, are not per frame. You don't need them to be per frame at all. So we will create them before all of this just to separate those things. Pipeline, call it be a bit more explicit, triangle pipeline. Because we have hard-coded the fact that this is a triangle. The first thing we need to do is to load the file, the output file of triangle. I will just do this and I'm going to take a look at how the file gets produced. So the compilation is not built into the system. You can't see that file right now. Hold on. So this compilation for slang is not built into Visual Studio. There is an extension, but the extension only provides the syntax highlighting and autocomplete. The building is done using properties where you have a custom build, you see. So item type, you say custom build tool, it will create a custom build tool here. And I've said, okay, slang compiler, which I've installed on my system, take the full path of the file, do a profile, we'll come to profiles later, target spirv, and output it as file name.spv. SPV is the spirv extension file name, and that's the output. Now let's find that. So we will actually open this, not this. We'll find this. Open with, not open with, showing. Interesting. I don't open folders quite often, and this is rather interesting that it actually doesn't show me that. But okay, it just produced the spirv file right next to where it was in place. We don't want that. So Visual Studio custom build binary path and custom build tools that outputs in the local directory, but there is definitely some options for this. Changing path for custom build step there. Oh, that's seems like the wrong kind of path, doesn't it? Well, we can look at this. MS build custom path. That is the DirectX shader. You see, like people actually use it for DirectX as well. The built-in shader is FXC. It's the old one, while modern shader is DXC, which is open source. It was quite nice. So you can see it produces all of that. That's error processing and all of that. But where is the paths? I should have paid attention to that first. So input is PS, output is PS. These are .h files. Custom build. Think I missed the part, huh? Incremental builds. Invoking the tool. Custom target. That doesn't seem to be telling us what the path of the output is. Well, output path, nothing, output. Okay, let's, it might actually be the other thing that I've ignored so far. General. So when this is done, dependencies output as content. Perhaps apply. Build solution. All success, no failures. That's not the extension. Okay, SPV is still here. Open in File Explorer. It's 86, debug. That's the Blaze executable that we have. And there's a text file. This is the exe recipe. Where's the executable then? Those are logs. Blaze. x86-64 debug. Blaze right there. Clearly the content flag didn't do much. Properties. It's the wrong one. Get back to solution view. Look, solution view. Properties. No, it's not a spent out. All right. Compile link slang shader. Okay, let's just find this. Represented by outer. Okay, let's check that, shall we? Properties, outputs is outer slash, and similarly here I'll add outer slash apply. Okay, build the solution. Well, all succeeded. Folder view, still the SPV, but that's normal. Show an explorer, CD6, debug. Nope, that's the wrong one anyway. CD6 debug plays, and that's triangle SPV. So this is fine now. Good to go. We're gonna delete this and build. Go back to Blaze, build solution, go back to folder view. Okay, so you're producing it here anyway. That is good. Okay, now that the slang shader has been completed, compiled, sorry, we will read it. So STL file system storage file size. Yeah. As a way to get SDL to load files for us. That way we don't have to deal with any other STL load file, you see. We don't have to deal with anything else, which is quite useful. Data should be freed by SDL free. So SDL load file, there it is. There's an async version of it as well, which is pretty cute. Cute. Load file, this is triangle.spv. Data size will be data size D, data size, and output would be void pointer of data equals that. Right. And I will not leave this data alone. What I would do is I'd create a stud span of U8. So U8, 8T. STD span will include it. And that is the actual data, which is going to be placed up here. I will actually load this like that. So span is a way to put both of these together in a single encapsulation. Actually, it doesn't matter. Let's not bother with that. But, if I was doing this on a larger scale, I would put spans. Makes it cleaner for me to handle things. SDL, free, and data goes in here. That data in the documentation was written that you have to free it. You see? So SDL is done and you should free. If there is an error, it will return null. So assert data. Of course, there's an error logging. Perhaps we should do that. So if not data, so null pointers will be automatically handled here instead of having to do null. I do believe it's recommended to use null pointer equivalence to be obvious about it. But I prefer using not anyway. Or perhaps that not. Just to be easy to read compared to the exclamation mark, which can be a bit difficult to understand. So once data is not available, then SDL get error will give us the error. We can just do an SDL log error and SDL category. So SDL log category is render. It's not actually render though. Is there a file option here somewhere? System, right? So we just log that error there and we move on. We actually assert false. Get error has some problems. Oh yes, we need a format string here. %s and then the SDN error next to it. This will also abort. So, we're gonna use the normal abort tag here. Now, the data is available to us. We need to load it into Vulkan to be able to actually read it. So let's look at that. It's known as a shader module. So shader module, you see? We will have two of them since we have written a vertex shader. So we have a vertex shader module and we'll have a fragment shader module. Then we will create these shader modules. So first, let's do it for vertex shader module. What we have to do is create shader module device, shader module create info. Oh, longer name, right? Null pointer, that's much shorter. Vertex shader module. DK shader module create info is shader module create info equals braces dot designated initialization vk structure type shader module create info. P next is null pointer because we don't have anything. Flags are 0. Code size is data size. Code is data. Okay, there is a little cool thing here that we look at. So first, it needs to cast. So we will cast it. We'll also get constant here first. So we don't need to have it as a void pointer. And we can have the UL32 right here. So we will do that. Data, it says cannot initialize it with a void pointer. So we'll do a cast here. Static cast because we know it can be cast into UL32T because, it's an existing file. Oh, yes, a pointer. We will assert that data size is modulo 4 because void pointer, like load file, will always load in bytes. UL32 is 4 bytes long, which means data size modulo 4 should be equal to 0. And that is a fact. Like if it is not true, this is wrong. Moving on, we assign the data here, no problems. Shader module create info is fine. I realize I don't need two shader modules. We just have a single shader module because all of it is in the same file, right? So SPIRV allows you to have a single shader module that has many different entry points, many different functions. So in this case, we have the vertex main, which is a vertex entry point, fragment main, which is a fragment entry point, and so on. But GNSL only lets you have a single main entry point. It has to be called main. So you will have to load two different files. But because people like having multiple things here in the same thing, so that you can share the structures available, lot of tools actually used to take the entry point, strip all the other entry points, and put them together, right? So they would have another thing here like @shader to say what shader it is. Then the system will take one of the shaders, strip out every other thing, put back the common data structures, and that becomes your new shader file. And that will be loaded into a GLS, like the, Vulkan internal thing. Instead, what we can do is we can use new languages like Slang that do have multiple shader options or multiple entry point options. and compile to SPIRV, which also has multiple shader options. Okay, seems like they prefer to have it as white pointer, but yeah. So multiple shader options keep working, right? I'm gonna call this raw data. So now we've validated that the data is correct so far. So now we can do your WP pointer, so constant pointer actually. Data equals static cost. Let me show you something interesting, right? And that's it. Automatically generates that. And this is one of those places I prefer having an auto because the static cast already tells me what this is going to be. And this one takes raw data instead. Cool. So shader module has been created here. This can fail. So we will do EK check as we always do. And that creates us the shader module. We don't need to put this in braces anymore. And we'll move the shader module down here. All right. Next step after shader module has been created is to link together shader module with other shader modules. Well, in this case, we are only using one, so we don't care. And create the pipeline stages. We'll actually go through this in the reverse way. So we can graphics pipeline create info, const graphics pipeline create info equals dot. And you can see this is massive. I mean, it doesn't look so massive, but you'll see soon. VK structure type graphics pipeline create info. T next is null pointer for now. Flags are 0. Stage count is 2. 2 stages. And this requires pipeline shader stage create info, right? We are going to change this. So we'll come back to this in a second. std array vk. We don't actually move that either. So stages equals braces vk shader stage. Let's vk pipeline shader stage create info, because this takes shaders pipeline. What? No, wait, wrong one. Pipeline shader stage create info, right? So shader stage create info, brace open, dot designated initialism again, ek structure type pipeline shader stage create info. T next is null pointer, flags are 0, stage is vk shader stage. So these flags are reused everywhere. The core flags are something like fragment, compute, and stuff, but you have all graphics, which will be fragment and vertex and tessellation and geometry and so on, while compute will be excluded from that. And so, you have to be careful to select the right flags here. In which case we need, we had vertex right there, but here, vertex bit. So that's the vertex shader module. So we give it the shader module. As you can see, how does it know which one is the vertex shader? It does not. So what it needs instead is the name, which in this case is vertex name, right? Specialization info, we have nothing. So we can leave it null pointer. We copy this, comma, paste again. That remains the same. This changes into fragment bit. See? This changes to fragment main. Right? That becomes stages. Stage count is stages dot size dot static cost. It automatically does it for me. I don't have to bother too much, which is quite nice about using IDs. Vertex input state, null pointer. I don't think you can have it at null pointer though. Let's check the spec. So input state, the pointer can be null if it is created with a vertex dynamic state. We're not using dynamic states for this, so this cannot be null. It has to be a pointer to vertex input state. So vertex input state. And we will have to create the vertex input state now. What type is this? It's inputs pipeline vertex input state create info. It's so small a name, isn't it? Equals dot as an initialization, pk structure, type, pipeline, vertex, input state create info. Look, I totally devised it. Input state create info. P next is null pointer, flags is 0, vertex binding description count is 0, so that is null pointer, 0 again, null pointer. So what are these description counts? We take input, and the only input we take for vertex shader is the index ID, which is built in. So we don't have to bother with it. But if we're actually passing vertices into the system instead of, baking it in, if we're actually doing it like real world, we would create a vertex buffer. And then we would have to describe that vertex buffer here. And we would tell, okay, the position, which is the first field in the vertex buffer, is at this location. It has this format, and so on and so forth. We don't do all of that right now. We don't have to bother with any of it, because you don't have a vertex buffer. Otherwise, you would also have to tell, okay, one vertex has this size, so each vertex shader will get that data. This data gets split by using the particular offsets, and so on and so forth. Again, we'll come to that if we come to that. I don't use input state much. Anyway, so vertex input state has been created. Next is input assembly state. Let's see if assembly state is compulsory. It probably is. It can be null if it is with dynamic state primitive we start, right? Which we don't have again. So vk pipeline input assembly state create info, const expression. This one will be a const expression as well. Input assembly. I know the naming isn't constant. It's fine for now. vk structure type pipeline input assembly create info. The next is null pointer, flags is 0, topology is vk primitive topology triangle. So these are different kinds of options. A triangle fan means you start with vertex 0, you go to vertex 1, then to vertex 2, and then back to 0 automatically. Okay. All you will say is 0, 1, 2. It recognizes that 0, 1, 2 completes a triangle and finishes it. Then you say 3, and now it knows that 0, 2, 3 will be the next triangle. Okay. So it does like a fan where one vertex at the bottom of a hand fan is common, while the other vertices are like the other part, the ends of each of these fans pieces. Let's actually look at one of these hand fans. Folding hand fan. Thank you. Image. Yeah. So this is how triangle fan works. This looks better actually. So 0 is here, 1, 2, 3, 4, 5, and so on. So 0, 1, 2 becomes a triangle. Then you say 3, it knows 0, 2, 3 becomes a triangle, and so on. This lets you do a lot of compression in the data. The other options are, so vk primitive topology. They're going to exclude the lines and points because those are lines and points. We're looking at triangles only. Triangle strip is something similar, but it expects you to add strips. So we can look at our triangles. Actually, let's just search for triangle strip. You see, it's already written in computer graphics. 0, 1. That's not the best thing. Let's look at Wikipedia, right? So you go from A to B to C. Okay, that becomes a triangle, just like a fan. But B is not considered as connected to A, but instead it's considered as connected to the previous two. Okay, now the previous two is C and D, so E is connected to C and D. Then D and E fall in the next edge that F will use. So the next after this would be FE connecting, right? So that forms a strip, if you notice. If these were all evenly placed out, this would become an exact rectangle strip. You have to be careful with these because this actually depends on how your vertex buffer is laid out. In our case, because we only have a single triangle, we actually do not care whatsoever. So primitive topology triangle strip or triangle fan. Triangle list, sorry. A triangle list is 0, 1, 2 is one triangle. Then 3, 4, 5 is one triangle, and so on and so forth, right? So you explicitly list each triangle. As you can notice, that wastes memory because let's take the triangle strip example. If you were to draw this using a triangle list, we will say ABC. Then we will also say BCD. So B has been repeated twice. Then we'll say CDE. Again, C got repeated 3 times already, right? And so on and so forth. So basically, we repeat vertices multiple times when we do triangle list. While triangle strip was cheaper, triangle fan was cheaper, but then triangle list is much more versatile. Primitive restart enabled is false. This is a 32-bit false, so I use the VK files. And we provide this. So input assembly goes in there. Next is destination state. Let's see, destination state is a pointer can be null if it is with dynamic. Again, create destination state. Pipeline, destination state, create info, const expression, destination state equals braces, yada, 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 S type, structure type, test pipeline, destination state, create info. P next is null pointer, flags are 0, patch control points is 0. Yeah, that's destination state. Wait, are we certain about this? Destination state is a pointer used by residential. It can be null if it's created with dynamic state set. So not created with dynamic state set. So yeah, unfortunately, we have to write the destination state here. And the destination state. So this is one of the places where the C++ version becomes quite useful because this is default, right? Other than the structure type, everything else is 0, 0, 0. So that is just default initialization. Even the structure type is default initialized. So instead, you just say destination state and you just close it, right? And it's much easier for us. Pipeline state, viewport state. This viewport is built alongside the size of the window. So a viewport tells you how much of that surface do you actually render in. So I can have a viewport that is 1/4 the size of the window, and it will only render on that 1/4, right? So if I actually need a split screen game, I will create two viewports and I'll render on both of the viewports separately. Binding this into a pipeline makes it very hard coded, which means every time you resize, you need to recreate pipelines. That is not good. So viewport state is the one place where I will say null, and we will use a dynamic viewport. As you can see here, viewport state again will have a viewport state. Viewport state, it can be null if it is created with viewport state. Yeah. Hold on, let's look at this. Oh no, it cannot be null. It has to have a viewport state. That is compulsory. Viewport state itself is compulsory. We care viewport state because it needs to know how many viewports we actually will use. There's initialization. Viewport state create info. The next is null pointer. Flags are 0. Viewport count. So how many viewports do we have? Just one. What are the viewports? Null pointer. Okay. Scissor count. We have to have one scissor. What are the scissors? Null pointer again. Both scissors and viewports are related to how much you can render. The difference between them is viewport just says render here. Okay. So viewport that is 1/4 of the screen will shrink everything into that 1/4, but you can still see everything properly. A scissor that says 1/4 of the screen, but a viewport is full screen means the scissor will only render that 1/4 of it. It's scissor, right? It cuts out that much part from the viewport that it actually shows. Of course, it doesn't actually render the rest. It will optimize it by doing this. But that makes it a bit cheaper than actually rendering everything and copying it, right? Not even bit, it's a lot cheaper. It has its own uses. But anyway, we need to put scissors and viewports. These are going to be dynamic. I will write a to-do here. To-do, actually not even a to-do. I will write a uncompilable thing. So static cast, not static cast, static assert uh, false. So this will not compile. Would dynamic viewport. Okay. It's just not going to compile. Even though this is compiling, but that will make us check it again later. This will come to it later. Rasterization state. Rasterization state. I'm going to stop talking now because a lot of this is just more or less boring work. Polygon mode fill just tells us that we have to fill up the polygons. If we don't do that, it will just be lines. So we get polygon mode line. Let's just draw lines. And rasterizer will only, do the edges. And points will basically get rasterized, don't do anything, we just draw points. Cull mode. We're going to do cull mode back bit. So this is back culling, which means if you're seeing the back of a triangle, this will erase. It won't, show you the triangle. Actually, let's leave it to now. Right now, we don't care because place is counterclockwise. So right now, we'll just show it even if it's reversed, but we'll come to that later. Depth bias enabled is false. Depth constant factor, we don't care, but we'll write it 0. Depth bias clamped, we'll write it 0. Split factor, we'll write 0. Line width is 1.0. Yeah, that's the rasterization state. So this is all the rasterization customization we get to have. So yeah, one of these we don't particularly care at the moment because we're not using sample shading. This is multi-sampling, anti-aliasing. They're not doing all of that at the moment. So sample master node pointer because we're pointer. Alpha to one coverage. False. Yeah. False. Ampersand multi-sample state. Depth stencil state. Again, more of this. Depth. We are not using this, so we will not test depth. We will not write depth because we need a depth buffer for that. Depth bound test enable which is false. Social test enable which is false. To stencil not stay. See. Finally is colorblind state, which is about colorblind state rate of flow, which is about transparency and stuff. So if you have multiple different things, how do we blend their colors? How do we mix the top color with the bottom color to show transparency? In our case, we just say we're opaque. Next is null pointer, flags are 0, logic up enabled is VK false, logic up equals region feature logic. There should be a 0 option for that somewhere. Doesn't matter anyway. Attachment count, 0. The attachments. Yeah, I think I need to put the attachment counts, eh? Let's check the docs. Yeah, it can only be done if we ignore, which we can't. So guess what? Pipeline color blend attachment state. Blend enable, VK false, we're not doing blending. Source color factor, again, we don't actually care. So we actually don't care. And in reality, it shouldn't be reading all of this. Technically, we should be able to remove all of it. But I like to leave it here, at least for now, because that allows us to come back and correct it later. Blend factor, destination alpha, not constant alpha units. I want source alpha. So yeah, basically what I'm saying, and this one should actually be 1 minus 1 minus source alpha. What I'm all I'm saying is, if this says 70% blend factor, then this is 70%, and the remaining 10%, sorry, 30% comes from whatever was already there. So it's opacity rendering effectively, color blend up. And so as both of these are multiplication is done with the factors, you just add it, right? Source alpha blend factor, okay, blend factor. Yeah, I'm making a mistake here. The attached flow state, blend factor, which blend factor is used to determine source factors. Hmm. Well, you can do source alpha and destination alpha. Source is so what is the alpha of the final product? We don't really care, but we're gonna just write source alpha, right? Destination alpha blend factor. We just say 1. Actually, we will put this as 1 and this is 0. So the alpha is effectively just the new alpha. Okay. Blend dot. Just set, I think. Yeah, we can just add that. It will just say, it will just set to 0 effectively. Color right mask. Yeah. Color component flag. Or, and we will just do RGBA. G B A comma. My formatting guidelines require me to do that. Not very nice looking right now, but we'll get that. Also, this, yeah, that's what it is. That's what I must start. Okay. RGBA, the attachments. We have one attachment and it's called colored attachment state, right? Blend constants is 0.1. Is it 0? Yeah, it's float. It's 4 floats. 0.0f, 0.0f. So it's when you ask for a constant in the state, this constant is what will be pulled out. Okay. Color blend state is here. We give it in state. Now comes dynamic state. So this one we have to do. Dynamic state. Yeah. State equals. Did I make a mistake somewhere? Takes dynamic state create info. Sorry. We create dynamic. Pipeline. Dynamic state create info. Once txpr dynamic state dot structure pipeline dynamic state create info next to 0 flags null pointer. Didn't I make a mistake there? Null pointer flags are 0. Dynamic state count. We have 2 different dynamic states. Which dynamic stage do we have? So we have the, actually we can do it with std array dynamic states equals bracket open, close that. VK dynamic state viewport and VK dynamic state scissor. So both dynamic viewports and scissors are dynamic. So we added that. Dynamic states dot count is size actually. Static cast it. Dynamic states is dynamic states dot data. That should get the job done. State create info. This is the only one with the create info thing because it already has a state in its name. Layout. It requires what is known as a pipeline layout. So what is a pipeline layout? When we have inputs to the shader, we need to provide locations to those inputs. So we need to say this input will be at this location so that the GPU can actually put the data there where it requires. All of that is put into pipeline layouts. So many pipelines can share the same layouts or use compatible layouts. And those compatible layouts would allow us to just keep things bound. So you put a thing at location one, and if two layouts are compatible at location one, then you can just keep using that same binding. We won't be doing any bindings in this engine. We're doing bindless, but we do need a pipeline layout. It's frankly speaking compulsory. However, it is also relatively trivial for the given thing. Because pipeline layout, VK create pipeline layout, device, layout, create info, null pointer for the allocator as normal, and pipeline layout goes in. This is VK check. VK, we leave the pipeline layout there, but VK pipeline layout create info and this expression pipeline layout create info equals structure type. Info, next is null pointer, flag is 0, set layout count is 0. So we're not using any of the inputs. So we can just use 0 and null pointers and get it done with. So that is pipeline layout create info. We'll pass it here. This pipeline layout, we will need it from the outside. Not for triangle, let's say, but we will normally need it. So I'll just move it out there, right? We create the pipeline layout. We're done with that. Move all the way down. So layout would be pipeline layout. Render pass would be null pointer because we're using rendering. Subpass will again be null pointer. Then subpass is an index. It was 0. Base pipeline handle 0. Base pipeline index 0. And this will actually be null pointer. Because you can actually have multiple pipelines in hierarchies, like sort of inheritance sort of thing. But since we only have one pipeline, what's the point of that, right? Take graphics pipeline create info. VK check. VK create graphics pipelines. VK create graphics pipelines, device, pipeline cache. We're going to give a null pointer there. Pipeline cache allows us to cache things so that next time we run the whole thing, pipelines are able to be recompiled. Create info card 1, because we're only making one graphics pipeline. Null pointer on the allocations and triangle pipeline as the input here, right? VK check. We just add the VK check there and we're done. Okay, so this does create graphics pipeline and the pipeline has been created. So we're all good. What's your problem here? Sensor of state is the whole state. You can just create default like that. I don't know what's inside, but I don't particularly care what's inside. At the moment, at least. However, since we have created pipelines, we need to destroy them. They are after swap chain before image view. VK destroy pipeline. Device pipeline is triangle pipeline and no allocation callbacks. We also need to do layout. So device pipeline layout and allocation callback. So layout is used by pipeline, so we'll keep it alive until after pipeline, right? Did we create anything else that has to be deleted? The answer to that is yes. We created shader modules right here, create shader module, and we haven't deleted it. However, unlike pipeline and pipeline layout, the shader module is used at this point, right? When you create graphics pipeline, the shader module is already used. We don't need it anymore. So we can actually destroy shader module and just destroy it right here, right? So that's done. Shader module is gone. We have cleared up as much as we can have. So that creates a pipeline. Once a pipeline has been created, we can actually render it. So command bind pipeline. So bind pipeline says that, okay, command buffer, use the pipeline I'm talking about. Sorry, it's a bind point first. So bind point is okay, pipeline point graphics, whether it's compute or pipeline. So whether it's compute pipeline or graphics pipeline, you don't know. So you need to tell it that the bind point is graphics. We take command draw. So normally you will bind other things here, but we are not going to do that because we don't have much, right? So the draw actually has instances. So how many times do you want to draw this? So you can say instances 4, and then it will actually do the whole thing 4 times effectively. But you'll need an instance level input as well, which we don't have, and we're not using it. So it's fine. Okay. So this is drawing. It's probably going to have errors and fail something, but we'll get to it. Does not have static storage duration. So it can't be const explosion. I could have just done a static and it would work, but it particularly doesn't matter that much, whether it's static or not really. This can be const expression, so we're going to make it const expression. But again, it won't be const expression here. It will just be a constant. Succeeded. Let's open the configurator to see if we have any errors in the thing. We did abort. Triangle or SPV could not be found. Abort. Okay. What's wrong with triangle.spv being available on that? My guess is that the binary is being run from the source directory as the working directory. So if I left the build output to the original output, they would be just fine. Let's check that. Properties, custom built-in. So if you remove outir, you remove outir, apply, okay, build solution, and we are in. SDL3 was not found. How can that be? I mean, so far SDL3 has been working for us, right? So how can it suddenly stop working? SDL file system. Let's see if this makes it work. Yes, it did. All child objects must have been destroyed. What have we not destroyed? Semaphores and fences. Okay, let's get into something, other things that we have as a bug in here. We haven't destroyed semaphores and fences that we created. VK semaphore, image acquired semaphores, destroy semaphore, device, semaphore, null pointer. And we need to copy, paste it twice because we will use it for render semaphore. And we have to do it once for fences. Fence. 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 And fence. The formatting here is right. I need to look at the formatting once just to ensure it's correct everywhere. But yeah, so that should be fine. Another thing is this is asynchronously happening. So GPU is still using the semaphore. We cannot just ask it to be like, okay, can you know, close the whole device? Because there are semaphores and frames, fences still running. The answer to that is to use VK wait device idle, device wait idle, sorry. Or you can do queue wait idle because we're running on the same queue, so we can wait for the direct queue to be idle. Or we can wait for the entire set of frame fences that we've created to be idle. So what we can do is we can move this deletion up here. And we can say we can wait for fences. We can move this up one step. Wait for fences, device, fence count is the number of fences, so frame and use fences dot count of size dot static cast. Defenses is frame and use fences dot data. Wait all is recreate true. Otherwise, it will just wait for one of it. And timeout is max value. So that's SCD numeric limits and 30 to T max. Okay. And that should wait for the fences. This scan timeout. It's kind of funny that if it times out, it crashes, and all we want right now is to shut it down anyway. So we don't particularly care if it crashes or not. The resolution, it shouldn't give us all of the warnings anymore. Yeah. Where is it? Okay, all child objects must be created. Command tool. We have forgotten to do command tool as well. Hey, image view. Command tool can be here. So auto command tools. Destroy tools. Destroy command tool and we give it command tools, right? That should work. Let's not give it again. Even though it's completely fine. Succeeded again. Let's go to the bottom, see if there are any validation errors that are happening right now. Command buffer must be in initial state. Another bug that we have caught. So you see, validation layer are very useful to find these kind of things. The problem that is happening is, so if you notice here, it says command buffer attempts to reset implicitly because it does begin. But this doesn't work because command buffers need to be in initial state unless, sorry. So you cannot do it without a reset command buffer bit because it is trying to independently reset each command buffer, which doesn't work. So instead, what we do is at the top of the frame, all resources are free. So we are resetting things here. So we can reset command tool. Okay. That allows us to actually reset the command tool that we're going to be using this frame. So command tools and frame index. So that is the current this thing. And we reset it. So okay, command reset flag. Nothing. We don't want reset resources. If we actually give away the resources, that will cause trouble for us because that will free all the memory and then you'll allocate again. That's going to be a performance hog. Does reset fences have timeouts? Well, I don't want debugging. Sorry, as a result, it does have results. So we check and run this. So does not have fragment state, but fragment state has been asked. We made a mistake somewhere. Beside the pipeline creation, I think I rushed a bit. This is a fragment bit. That is fragment main. This is stages are fragment. So what's your problem then? Stages, the data, stages dot size, stage counts, stages, that should be fine. Does not have a fragment shader state. Was there an error somewhere up there? Yeah. So here we have shader state fragment bit. What mistake am I making here? You can check. Hello, pipeline state. Okay. So stages, stage create info. The pipeline stage, P name is entry point name for the shader. Show the code for the stage. Stage is flat widths. No, that should be fine. Tensor 0 does not have a fragment shader stage. Why would it say that? If I is to do, this will be 2 and that will be the value for that. It comes from the data of the stages. Stages are up there. The data for the stages is 1 and 2. Shader model has been provided. Fragment bit is here. Tracks are fine. The text name, fragment main, are those not the names? Fragment main is the name here. So what's wrong with it? Okay, what we can do is we can actually check what the error is. And up here, pasteurizer discard enabled, did we set it to true? That would be funny. Yes, we did set it to true. Nice on Vulkan to actually tell us this problem immediately. Okay, manifest fire, yada yada yada. But there are bugs still. Circuit layer, that's fine. Dynamic viewports are used but not provided. So we don't have dynamic viewports, even though we said we will be providing them dynamically. So let's get to that. What is a dynamic viewport? A dynamic viewport is just a viewport that is provided during this render pass. So once we start with the rendering, so rendering has started here, begin rendering. We'll put the braces, as I said, like I like the indentations between these. So begin rendering, we can do vk command set viewport. It will take the command buffer, the first viewport, which is 0, the viewport count, which is 1, and it will take the viewport. vk viewport equals, there's an initialization. X is 0. We wanted to start at X. Y, if you put it 0, that is fine. That is normal, right? So it says top left is the 0, 0. Height, width is the size of the swap chain. So we will actually use the swap chain extent dot width, swap chain extent dot height. Both of these need static casts. So we'll do that. Min depth is 0.0. Max depth is 1.0. Okay, so far so good. This creates an image with y as negative. So there is a little key to solve this problem. The answer is to negate the height. Okay, so the height is negative and it flips up. So it starts from origin and it goes upwards. This is supported in Vulkan. A negative height was added simply because people did not like the y negative thing. This will cause a problem though, because our origin is still at the top left corner of the screen, which means the rendering is happening above where our screen is. So in reality, y has to be set to the height itself. So swap chain extent dot height static cast, right? So now y has come down to the bottom and then height is negative and it goes back to the 0, right? So we come from bottom left corner and then we move upwards. And that makes the height positive. So that is the viewport we'll be using. Next is vk scissor, which is actually just a vk rect 2D LA. Scissor equals that. It takes an offset, which is nothing but 0, 0, 0. It takes an extent, which is nothing but swap chain extent. Right? What's wrong with the, oh, it's 2D. It's 2D. Forgot about that. There's also 3D versions of these things. So instead of viewport, we will allow to scissor. And we will take scissor here. That should do it for that particular thing. Let's continue watching what the bugs are. Okay, rendering info color attachments, VK image view, but pipeline was created with rendering create info color attachments equals undefined. Dynamic rendering. Can look at the tutorial. Let's go for that. So that's the rendering info. It's fine. Pipeline creation needs something different. That's a P next. You see, it means that P next. So pipeline creation, we get pipeline, read, graphics, pipeline create info. And we do that. East const superiority, so const goes to east. Elder, here, info. Hey, this looks wrong. No, it looks fine. Yeah, so P next actually will get rendering create info here. And swap chain image format is something we need to pass into this normally, but we already have the format up there somewhere, right? No, we don't. So let's look for the format. Not the right format. It's right here. Is it not global? It is in fact not global. So we will move that up here. VK format. We'll just move the normal format, right? Option format. Uh, Inside here, we will say swap chain format equals format background. And now we can use that version. Swap chain format version as a color attachment format, right? So that is the format we'll be using here. Yeah, and the creating the computer pulse expression. Yeah, it's gonna do that and then complain and build the solution, send it. Oh look, triangle. Huzzah! uh there we go. We have it. Not expected to come out this time, but we knew a bit more. So position.rgb clearly is not working. And it, as you saw, like the color that we actually got out was this weird whitish color. The reason for this, I don't currently know, but let's try outputting a red and we can see from there. So this should output exact red. SDL3 is not found. Build system. Play that here and there. It's quite interesting, is it not? Build rebuild solution. And run. And it just runs. You see? Like, what's wrong with the linker on this particular thing? I don't get it. But anyway, so that's the triangle. It is in color red. So what's the issue with this particular thing? I think it's because SV position works on screen space. So this is not actually what we want. It's actually giving us between 0 to 1280 on X. And you can try that actually. So we'll take RG, we'll leave blue as 0. Or you can leave it as 0.5. And we will actually will divide just R with 1280.0 and position dot B. Sorry, my mouse is affecting the view. 720.0. So that should actually give us the solution. Maybe. Yeah, purple shade because it's in the middle of the screen. But yes, that seems to be the issue. So what we'll do is the very thing I said I can do at the start, which is struct vs out, vertex out, depends on what you want to call it. And we put the vertex position here. So node 4 out position is a SV position struct. And the same one as a float 4, which has a course position, which has no binding to it, right? So I'll just write here. It doesn't have special bindings. And so I'll just write position with this, or screen space position. NDC position. There's so many names you can have, but it's just a name. It's literally just a name of the tentacles. Okay, so vertex out is done. And now instead of returning this, okay, you can actually use the C version of things with this, or you can do a trailing. Both of them are completely fine with being slang. We shall not bother with things. So out position is vertex Hmm, how else is it with a bracket 0.066 0.08666? Does this compile? It does compile. That's quite nice. But let's do it. Let's do it in the way I know how to do it properly. Text output, dot out position equals vertex pause, vertex ID, or it's ARSE. Supposed to be ARSH. It's the same value and you return output. Now that when you go here, we can actually just ask for the exact MDC position that we're using. LDC position, and you build it. It will automatically use those positions. Right, this SDF thing is bugging. I need to fix it, but I'll do it off screen. But yeah, that is just blue. It's purely blue. And the reason is simply because we divided here. So let's go back to the RGB, build solution, and then pass. Come on. There we go. Now we have some amount of colors on most of these sides, right? And so at the center, it will flip from 0 to a positive color because our normalized device coordinates are between -1 and +1, or in this case, -0.5 to +0.5. What we can do, and we shall do actually, is to not output the positions at all, but instead output colors. These shall be red, green, and blue. And point 0.0f, 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 and 0.0f. Those cut, paste, 0.0f. And this one is two of them. I'm just going to copy from here. And this is to get rid of all of these. No problems. Okay, and instead we can say vertex color. So vertex color, and we can replace vertex pause with the vertex colors here. And then here we will ask for interpolated colors, which is nothing but the vertex color. Right? We will do a thing, not call it vertex color, but we will use color. I don't know the name of the scheme. Some people have a different name. I'm fine with this, so I'm going to use that. Ah, SDL. Come on. Welcome to Vulkan. Hello, world. That's it. We're done. Have a good day, people. We are going to stop right here. Everything seems to be fine, except for the semaphore, which is currently unused. And so we cannot destroy it. We'll actually fix this bug first, I guess. So let's not bother with actually waiting for those fences, because I suppose something is happening that's not correct. Device wait idle, device. Okay, check. And we do nothing. We just like totally tell the device to just wait. Because this is shut down. We care nothing about performance here. So we just wait, we just tell device, hey, once you're done with every single thing, we can delete all of this, right? Now we're done. So have a good weekend, folks. Happy Pentecost to those. And a bit too late, Eid Mubarak. See you guys.